Swayam Prabha. Digital India. Educated India.
Hello everyone, this is the third lecture of this week. Today we will continue the discussion we started in the last lecture, that is construction of shape function for higher order triangular elements. So if you recall, finally we arrived at this form for any triangular higher order triangular element having a kth node, having k nodes per side, means in one side we have k nodes. Then the shape function for any associated shape function associated with any node can be represented like this, where fj are the function of L1, L2, L3, and fj is this is the fj computed at the particular node, and L1, L2, L3 are the area coordinates. And once we take some example and write the shape function for some triangular elements, how to use these area coordinates will be clear. Now, so just again what we discussed in the last class, area coordinate means here, now if we take a triangular, we can have any number of nodes in between, but when we are talking about the area coordinate, these are associated with only this vertices, okay, 1, 2, 3. Now for area coordinate, L1 is associated with node number 1, L2 associated with node number 2, and L3 associated with node number 3. So how it is written? So this is our L1 for L1. So at this point L1 will be 0. So because if your shape function, if you take at node number 1, all this shape function has to be 0, all the nodes on this line number 2, 3, L1 will be 0, and on this point L1 will be 1, right? And this is, we are moving in this direction, and we have we can construct a local coordinate system S in this direction. Similarly for node number 2, if we take, then this is our coordinate system, and for this one L2 will be 0 and L2 will be 1. So this is the interpolation property, and then we have a local coordinate system which moving in this direction, S1 normal to this line 1, 3. Similarly for node number 3, we can have this is our coordinate, and here L3 will be 0 and L3 will be 1, and then in between we construct a local coordinate system S, which is normal to this axis. Okay, so these are L1, L2 and L3. Now we need to write the shape function in terms of this new coordinate system L1, L2, L3. Now, so if we recall, our shape function was in terms of area coordinate system. Shape function, the expression of shape function is this, and this, when we write, this expression will become this for particularly node number 1. Phi 1 will be this. So for phi 1, if we construct a local coordinate system like S here, so S0 will be 0 at that point. So there are kth node. It means that there are k minus 1 division. If you start from 0 here, S0 will be 0, and at this point it will be Sk minus 1, which is 1. And then in between, for any arbitrary node, say pth node, we know that Sp can be written as P by k minus 1, right? Similarly, S1 will be 1 by k minus 1, S2 will be this, Sk minus 2 will be this, and finally Sk minus 1 is equal to this. And then your phi 1 will be this. So we have discussed this in the last class, right? Now, you see, for Now we have to construct a similar local coordinate system S in the direct for L1, and again the similar local coordinate system for L2 and L3 as well. So therefore, instead of writing in terms of only S, taking S, the symbol S for all the direction, let us use the conventional notation we use, and we have already used these notations in case of quadrilateral elements, that is in terms of xi1, xi2, xi3 and so on. So what it means that, so it is very similar. In this direction we have constructed a local coordinate system S, and here it is S0 is equal to 0 and Sk minus 1 is equal to 1, and in between you have different values of S. Now instead of now S, we write it is xi1. Xi1 associated with area coordinate L1. So at this point xi1 will be 0 and at this point xi1 will be 1 for triangle, and this is the direction of L1. Similarly, for node number 2, here it is xi2 will be 0 and it is xi2 will be 1, and for node number, and then direction is this, normal to this line. And similarly for node number 3, xi3 will be 0 and xi3 will be 1. There is no harm in writing expressing the expressing S, using S in all the direction, but just to avoid any confusion, we are using different symbols in different directions, xi1, xi2 and xi3 in L1, L2 and L3 direction respectively. Okay. Now, so similarly for, so if we put all these things together, so this our area coordinates, 3 area coordinate putting together will look like this. So this will be xi1 in this direction, moving in this direction, this is this direction, and then we have xi2 which is moving in this direction. Xi2 is equal to xi2 will be 1 here and xi2 will be 0 here. Okay, there is a typo, and similarly xi3 is 1 here and xi3 will be 0 here. So the same thing, if we can extend to 6 noded triangle, it will be something like this. You see, now we have intermediate node, intermediate node at the boundary, and these nodes are placed. These nodes are equally spaced. If you recall, when we discussed the shape function, one of the important criteria we use is nodes are equally spaced. So let's talk about xi1. So only L1 direction. L1 direction is this one. This is our L1 direction. So xi1 will be 0 here and xi1 will be 1 at node number 1, and this node is equally spaced. So at this node number 4, xi1 will be half. Similarly, if we take xi2 will be 0 here and xi2 will be 1 here, and then this is for L2, and then at node number 4, L2 for coordinate associated with L2, node number 2 xi2, it will be half. Similarly for L3, which is in this direction, L3, xi3 will be 0 here, xi3 will be 1 here, and at this node and this node, xi3 will be half. Same thing can be written for other triangular elements as well, depending on the number of nodes we have on each sides. Okay. Now, so let us now go back to this. So this is the shape function written in terms of S. Now we have just now discussed, instead of S we will be using now xi1, xi2, xi3 coordinate. So for phi 1, the same expression can be replaced. So this will be the position of all the nodes. This is for L1 I am talking. So xi1 will be 0, xi1 is equal to 1, and this xi will be equally, these nodes are equally spaced. So then therefore this expression of phi 1 will be like this. So, okay, so L1 minus 0 means L1 minus this, and then L1 minus this, then L1 minus the next coordinate this, and similarly L1 minus this, and then denominator this minus this coordinate, this minus this coordinate, then this minus this coordinate, and then finally this minus this coordinate, which is same as this expression. Now explicitly we are putting the values of S in the direction of L1. So this is the phi 1. Similarly, if you have to write phi 2, phi 3 or other phi's, same expression can be written, but in that case the values of xi1, xi2, xi3 are to be written accordingly, depending on which node we are considering. Let us take some example and then probably things will be clear. Let us take first example of a 3-node triangular element. We know we have already derived the shape function for that. There is no new thing we'll be discussing, but to start with, just for the implementation of the area coordinate, to get the shape function for other higher order elements, I thought it is good to start with the problem which already we know what are the shape functions. Now for this, let us find out what is phi 1. So phi 1 will be what? Phi 1 will be, if you look at, so phi 1 will be, it will be L1 minus this node, means coordinate of this node is, means it is 0, okay, and then divided by, then the coordinate of this node. At this point we want to evaluate this shape function, so coordinate of this node minus coordinate of this node means 1 minus 0. This is equal to L1. So phi 1 is equal to L1. So we have seen that phi 1 is equal to L1, but the same thing can be written from that expression as well. Similarly, let us find out phi 2. Phi 2 will be what? Phi 2 will be L2 minus, this is phi 2, and the coordinates, the shape function corresponding to this node, this phi 2. So L2 minus this one, the coordinate of this node means 0, and then coordinate of this node minus coordinate of this node means 1 minus 0. This is equal to L2. Similarly, if you take phi 3 will be L3 means this is L3. So L3 minus coordinate of this node means it is 0, divided by coordinate of this node minus coordinate of this node, 1 minus 0, that is equal to L3. We have already seen that for a 3-node triangular element, phi 1, phi 2, phi 3 are essentially L1, L2, L3, which is again we have seen, we get it from that general expression. Let us now write this shape function for a 6-node triangle. So this is we already know what are these meaning. Blue lines are for L3, which is associated with node number 3, then red one is for L1, and then black one is for L2. Okay, so let us first write phi 1. So phi 1 will be what? So phi 1 means the shape function at node number 1. So shape function at node number 1, how to construct? It will be L1 minus coordinate of node number 2, because it is on this line, coordinate of node number it is L1 minus this is our, what is it? This is our L1, yeah, L1 minus the coordinate of this line means this is 0, okay, and then L1 minus coordinate at this line, right, and coordinate at this line will be half. So that is divided by coordinate of this line, means coordinate of node number 1 means 1 minus coordinate of this line, which is 0, and then coordinate of this line means I1 is equal to 1 minus coordinate of this line means it is I1 is equal to half. So this gives you phi 1 is equal to L1 into L1 minus half divided by half. So which gives you finally phi 1 will be 2 L1 into 2 L1 minus half. Now you check, it must satisfy the interpolation property. Interpolation property means that phi 1 should be equal to 1 at node number 1 and phi 1 will be 0 at all other nodes. So at node number 1, so all other nodes means, so at node number 1, you check your at node number 1, L1 will be what? L1 will be 1. So therefore phi 1 will be, if you substitute L1 is equal to 1 here, L1 is equal to 1. So phi 1 will be 1, right? Now at node number at nodes say 2, 5, 3 means 2, 3, 5. If we take L1 will be what? This will be 0, 0. So phi 1 will be 0. And at node number 4 and 6, at nodes 4 and 6 means on this line, it will be half. So L1 is equal to half. So phi 1 will be 0. So it is interpolation property, and again it has to satisfy it because our expression that we had written in the last class, that is based on this property, right? We tried to impose this property and got this expression. So our phi 1 will be like this. So similarly, let us find out phi 2. Now phi 2 will be, phi 2 is what? Phi 2 will be corresponding to this node, right? Corresponding to this node. So phi 2 will be L2 minus this xi2 will be 0 here. So it is 0, and then L2 minus the mid side node xi2 is equal to half, which is half, and then divided by 1 minus, means coordinate is xi2 is equal to 1 minus xi0, it is xi2 is equal to 0, and then 1 minus xi2 is equal to half, xi2 is equal to half. So this gives you phi 2 is equal to again L2 into L2 to L2 minus 1, which is same as phi 1 means the equation, similar equation, but it is in terms of L2, and then that was in terms of L1. And if you apply the same logic, you can show that phi 2 will be 0 only at, phi 2 will be 1 only at node number 1, and phi 2 will be 0 for all other nodes. Similarly for phi 3, if you calculate phi 3 means for this node number, so it will be L3 minus xi3 will be 0, and then L3 minus xi3 is equal to half for mid side node, divided by 1 minus 0 and 1 minus half. So this gives you phi 3 is equal to L3 into 2 L3 minus 1. So this is our shape function for all the vertices, node number 1, node number 2, and node number 3. Similar logic, if you apply, you will see that these satisfy the partition of satisfy the Kronecker delta property. Now let us find a shape function for a middle node, say node number 4. Now phi 4. Now look at phi 4 has, now at this phi 4 we have to consider both the coordinates. We have to consider this coordinate and this coordinate as well. Means phi 4, in order to get the coordinate shape function for phi 4, we need to consider L2, and then we also need to consider L1, right? So phi 4 will be, because on this line and on this line and on this line, phi 4 will be 0. So phi 4 will be first L1 minus, so this is our phi 4. This will be it is very similar to we had taken tensor, we call quadrilateral elements. We had taken tensor product to get the shape function for a quadrilateral element. It is the concept where it is very similar. Now our coordinates that we are talking about, they are not orthogonal coordinates, but we have two coordinates, and somehow we have to take the product of these two coordinates to get the shape function at node number 4. So we have to take the product from this the information from this coordinate and information from this coordinate. Let us first take the information from L1. So this node, if we take the in the L1 direction, means it is in this direction, L1 direction, the coordinate of this node is half, right? So the shape function will be L1 minus this minus 0 divided by coordinate of this node minus coordinate of the origin of L1, means it is coordinate of this node, means for I1 means half minus 0. This is the contribution from L1 direction. Let's take the contribution from L2 direction. L2 direction is in this direction. So if we take node number 4, what is the coordinate in the L2 direction? Xi2 is equal to half. So contribution from will be L2, means this minus the coordinate of this node, means it is 0, divided by coordinate of this node, node number 4, minus coordinate of this node. So it is half minus 0. So phi 4 will be then 4 L1 L2, right? Now similarly, if we have to consider shape function for node number 5, for node number 5 we have to get contribution from this coordinate, the blue one and the black one. The blue one is what? The blue one is for Xi3 and the black one is for Xi2. Black one is for Xi2, right? So the shape function will be phi 5 will be then L2 minus 0. So and then coordinate is half minus 0, and similarly contribution from other coordinates L3 minus 0, it will be half minus 0. So phi 5 will be 4 L2 L3, okay. And final phi 6, this 6, if you have to find out, we have to take contribution from red one and contribution from blue one, right? Red one and blue one. So red one is L1 and blue one is L3. So it will be phi 6 will be L1 minus 0, then half minus 0, and then L2 minus 0, L3 minus 0 and half minus 0, right? And then eventually it becomes phi 6 becomes 4 L1 L3, okay. Now if you check whether it satisfies the partition of unity property or not, check for node number 6, L1 is equal to half, and at node number 6, L1 is equal to half and L3 is equal to half, node number 6, okay. So this gives you phi 6 is equal to 1. At other nodes, at say you take any other nodes, either you take the 3, 5, 2 or you take 1, 4, 2. At 1, 4, 2, at 1, 4, 2, L3 is equal to 0. So phi 6 is equal to 0. And at say you take other node, say 2, 5, 3, if you take 2, 5, 3, L1 is equal to 0, and that gives you phi 6 is equal to 0. So it satisfies the Kronecker delta property, and that is for other say function as well. You can show 4 and 5 you can show. So this is how we can have the shape function for higher order triangle. The example is given for 6 node triangle. Now you look at the shape function, if you recall, for a 3 node triangle, our approximation was linear, and therefore if we differentiate, take the derivative of approximation, we get a constant value. That's why it was called constant strain triangle. But in this case, you see it is a quadratic, and if you take the derivative of that, you will get a linear function, and this shape function, this element is called linear strain triangle or LST. Okay. Now if you have any other triangle for say 10 node triangle or any other node triangle, similar logic can be applied to get the shape function. Okay. Now last is, we have constructed the shape function. Once we know the shape function, we know the approximation over the each element. Now this is in terms of L1, L2, L3, or the shape function in terms of L1, L2, L3. These are our coordinate system. So when you get an approximation in terms of L1, L2, derivative in terms of L1, L2, we have to substitute this, we have to use this as an approximation of test and trial function and substitute in the weak form. So the weak form you get in terms of L1, L2 and L3. Then that weak form needs to be integrated, right? Now the question is, we know how to integrate a function of x and y over a domain we have we know the methods for that. We have discussed the Gauss quadrature technique, numerical integration, but at least the visualization we can do. But now our shape functions, all these equation, all these term inside the integral, inside the integration is in terms of L1, L2, L3. But they all are now the thing is, they all are, if they are monomial term, then these term can be integrated in an exact sense. And this is the expression. And if you recall this expression, we had seen similar expression during the lecture on Gauss quadrature technique, right? So L1, L2, L3 are the area coordinate, I, J, K are the power. So this gives you the monomial, a particular monomial in a polynomial expression. And this I, J, K are the power, and 2AE, AE is the area of the triangle. And we may have to evaluate the bound, we may have to calculate the traction term, so boundary integral is required. So if you have to integrate anything over boundary, over a boundary with a limit a and b, and that gives you this integration. So this, if we find that the term the term needs to be integrated, we can correlate this term with this, then we can get the integration from this, and then we don't have to do any numerical integration. Okay. So with this, let us stop here today. So we now know how to construct shape function for triangular element, higher order triangular element. We have derived the shape function in terms of area coordinate for linear strain triangle, but we know the procedure. So applying the procedure, we can get the shape function for other higher order triangles as well. Now what we'll do in next two classes is, since this week our major focus is to discuss the implementation of our computer program for finite element method for problems in two-dimensional elasticity. So next two class we will take up some examples. We will write a code for finite element method in linear elasticity, two-dimensional linear elasticity, and then see other implementation steps. Okay, with this, let us stop here today. See you in the next class. Thank you.